Great. So it is my pleasure to introduce our second speaker for today, Claudio Manzari. Hopefully I pronounced this in the right way. Completed his undergraduate studies at the University of Bari in Italy, and then he moved to Zurich for the PhD program in physics at the University of Zurich. Claudio got his PhD in 2022, and he's currently a postdoc at UC Berkeley and Lawrence Berkeley National Laboratory. In September, he will start a postdoctoral fellowship at the Institute for Advanced Studies in Princeton. And today, Claudio will be talking about Axion Signals from Supernovae. So take it away, and thank you for accepting our invitation.
Thanks a lot, and I'm very happy to be here, and thanks a lot for the invitation. So today, I would like to tell you about the recent work I've done with my collaborators in Berkeley, Benjamin Safdie, Bar Savarai, and Eugene Park. All of us are phenomenologists, mainly working on high energy theory. And of course, we had plenty of discussion with astrophysicists and cosmologists, but I would really like today to have ideas and suggestions on how to improve our work. We have been looking at detecting axion signals from the observation of supernovae. So let me start. Okay. So let me start. Is there a way to remove it?
Hide floating.
Yeah. Okay. So let me start introducing the motivation for our work. Why? What is the QCD axion and why it is important to look for it? So skipping all the details about the theory, the QCD Lagrangian has this term here, which is the only term that violates parity and its combination with charge conjugation. So given this term, you expect to see some CP violation in nature, in the strong interactions. However, current measurements of, for instance, the neutron electric dipole moments tell us that this parameter here, which is a free parameter of the theory, has to be as small as 10 to the minus 10 at least. And the strong CP problem is the lack of theoretical understanding of why this parameter has to be so small. Now, a class of solution is based on the following idea. If we have a pseudoscalar field A here that couples to QCD, as in the last term here, well, this guy will get its mass and its potential generated via non-perturbative effect of the strong interaction. Now, if you look at the potential and you try to minimize it, you realize that you have to minimize this sign. So this guy gets a vacuum expectation value, which is roughly FA theta bar, such that if you plug this result in equation 1, first and last term cancel, and there is no CP violation expected in the strong interactions anymore. So the QCD axion is this particle here that solves the strong CP problem. What I will refer to as axion-like particles are a generalization of this class of particles, where we have again a pseudoscalar field, very light, very weakly coupled with the standard model that does not need to solve the strong CP problem. Now, since these guys are very light and very weakly coupled, they are very well described by the classical field evolution in the early universe. So if you solve the equation of motion for this field A, you realize that at some point when the mass of the axion is roughly equal to Hubble, it starts to oscillate around the minimum of its potential. And this collective oscillation can behave as a cold dark matter. Cold dark matter with a number density that roughly 1/2 the mass of the axion times these two parameters. Alpha is the initial misalignment angle, and FA is another parameter of the theory, which is called decay constant. For the QCD axion, there is only one parameter in the theory, so MA and FA are in a one-to-one correspondence. For axion-like particles, that's not true, but except for this difference, they both can reproduce the correct dark matter abundance today. So the QCD axion is a very well candidate to solve the strong CP problem and can also explain the nature of dark matter. Axion-like particles, just the latter. So let's start to familiarize with the parameter space of these theories. This is the usual plot where we show the constraints that we have on these theories. We have on the x-axis the mass of the axion. On the y-axis, it's coupling to photons. So this is a coupling of an axion to two photons in inverse G. Why we choose to show the coupling to photons? Because it's a very minimal expectation, and because it's almost an unavoidable feature of this class of theories. Here you see these two lines being the theoretical prediction for two different QCD action models. So again, G gamma gamma and MA are in one-to-one correspondence because there is only one parameter in the theory, while in general, axion-like particles can populate the entirety of this parameter space. In green, you have constraints on this theory from astrophysical observation of, for instance, supernovae, neutron stars, white dwarfs, galaxies. In blue, constraints that assume that these axions constitute 100% of dark matter, and in red, constraints obtained from laboratory experiments. Now, from now on, I won't distinguish much between QCD axion and axion-like particles. I will refer to both of them as axions. So, how can we use supernovae to constrain this theory? Well, a first class of bound is called cooling bound. And the idea is very simple. You have axions are produced in the very first instance after the core collapse, where the temperatures and densities are very high. They are very weakly interacting, so they just free stream out of the supernova, bringing out energy, modifying its thermal evolution, and therefore modifying the luminosity evolution of neutrinos. So, for instance, we can use the data from supernova 1987A, where we measured a dozen of neutrinos on Earth, to constrain the axion luminosity. Roughly setting the axion luminosity smaller than the neutrino luminosity, we obtain, for instance, this bound in purple here. Now, this constraint turned out to be pretty weak, as they can constrain at most coupling of the order of 10 to the minus 18 inverse GeV. However, there is a second, more powerful idea. Again, axions are produced in the very first instance after the core collapse. They free steam out of the supernova, and then they can convert into photons in an external electric or magnetic field, giving us gamma ray signals. So we can look for these gamma ray signals. What we did in our work was to study in particular this kind of bounds from the data collected by the Solar Maximum mission, which was online at the time of the explosion of supernova 1987A, and we also worked on projection for future supernova. So, first of all, how are these axions produced in the core of the supernova? For a QCD axion, you must have a coupling to gluons. So this coupling to gluons will induce a coupling to photons. And here, for instance, you can see three different predictions for three different QCD axion models. You see that they are all very similar. Moreover, this coupling to gluons below QCD confinement will induce a coupling to nucleons. So you will have a coupling of this axion to protons and neutrons. Here at the bottom, you can see all the most relevant production mechanisms. First one is Primakov effect. You have a photon that converts into an axion, scattering off an electric field of an ion. In a supernova will be proton. You have neutron Bremsstrahlung, so you have neutron-neutron scattering mediated by a pion with the emission of an axion. And these last two diagrams are just a pion conversion into an axion, scattering off a nucleon in general. For a generic axion-like particle, you don't expect to have a coupling to gluons, just a coupling to photons. However, this will also induce a coupling to nucleons at low energies due to this one-loop diagram here. Now, the first thing that we noted in our paper is the following. Even though this coupling is suppressed by the fact that it's just induced at one loop, the large density of protons and neutrons compared to photons in a supernova, is such that all these diagrams are comparable. So even though you would have expected the first diagram to dominate, that's not true. You need to take into account all of them to properly account for the full axion emissivity from a supernova. So before showing you our results for the axion emissivity, let me just show you a few quantities needed for the calculation of the axion emissivity. Here we relied on the one-dimensional simulation for the supernova provided to us by the Gakin Core Collapse Supernova Archive. Here you can see the temperature profile for three different simulations that we use to account for the uncertainties in the simulation itself. They are named 18.6, 18.8, and 20, which are just the units of solar masses of the progenitor star. And they also differ by the mass of the remnant neutron star. So you can see that 18.8 is the coldest simulation that we used to extract all our bounds in order to be conservative. While for the projection, we use the 18.6, which is the middle one. These are the profile of the matter densities, and you can see that they don't change much among the three simulations. Other important quantities are the nucleon masses. Here you can see the proton mass as a function of the radius at 1 second post bounce. You see that it goes down by almost a factor 1/2 at the very center of the core. And on the right, you can see the chemical potential for different particle species, again, as a function of the radius. Here we have proton, neutron, electron, neutrino, and pions. And finally, you can see the lapse, the gravitational lapse factor 1 plus z, again, as a function of r at different times for the simulation 18.6. Again, also all of these enter in our calculation. And this is the general result. So I'm fixing the coupling to photon to be 10 to the minus 12 inverse GeV, and I'm showing the number of axion per unit energy as a function of energy, integrating over the 10 seconds after the supernova explosion. So first of all, in black, you have the result for a generic axion-like particle. You have a result for Primakov, Bremsstrahlung, and pion conversion. You see that the three processes are all comparable, and pion conversion dominates at higher energies. Then in blue, you have the result for a specific QCD axion model called KSVZ. So it is important to note that Bremsstrahlung and pion conversion are much larger here than for a generic ALP, because they are not anymore dominated by the coupling to photon, but by the coupling to gluons, and they are generated already at 3 level. They are induced already at 3 level. And they are much larger than Primakov, which of course is the same for both scenarios because it just depends on the coupling to photon. Okay, so we can start now looking at the bounds. First of all, we reproduce the constraint in the literature using the conversion of this axion into gamma rays in the Milky Way galactic magnetic field. So here in red, you see the result previously quoted in the literature that we reproduce almost exactly, where people only included Primakov effect in the axion production. And here we were using all the magnetic field model from Johnson and Farrar. And in orange, our updated result, where we use the most updated Unger and Farrar models, and the band accounts for the uncertainties in their modelization. And you see that the bounce is also stronger because now we are accounting for all relevant production mechanisms. However, even though we improved a little bit on this bound, we are very far from touching the QCD lines, which is the real goal of this search, because we would like to probe this region, which is the theoretical, the region where we can solve the strong CP problem. So the second point that we make in our paper is the following. Now, when these axions are produced, they are produced in the very first instance after the core collapse, and they free stream out of the supernova with a speed which is roughly c. This speed is much faster is much larger than the speed at which the electromagnetic current rearrange in the stellar plasma, so that when the axions escape out of the outermost layer of the star, they encounter still the pristine magnetic field of the progenitor star. So we could use the magnetic field of the progenitor star to compute the conversion probability of this axion into photons. So let's try to put some number to make some rough prediction. So if you study the coupled equation of motion of the axion and the photon, you find that once this condition is satisfied, condition about the mass of the axion, its energy, and the propagation length, the probability just scales as the coupling squared, the magnetic field strength squared, the propagation length squared. So for the Milky Way magnetic field, we have a magnetic field of micro-Gauss, propagation length of kiloparsec, and the probability you get is around 10 to the minus 5 J gamma gamma over 10 to the minus 12 GeV squared. For The stellar field, let's take supernova 1987A. Its progenitor was most likely a blue supergiant. Let's assume let's model its magnetic field as just a dipole with the field strength of 1 kilogauss. So for B we have kilogauss. For propagation length microparsec. You compute the conversion probability, you'll find something very similar. So what you expect is that the two constraint, like the constraint that you would get on this theory, considering the two different conversion probabilities, are roughly similar. However, when is this condition met? Well, for propagation to a stellar field, we have a much smaller propagation length, such that this allows us to probe much larger axion masses. And in fact, now these are our results for supernova 1987A, again using the data from the solar maximum emission. The dark orange region is the region I discussed before, previously discussed in the literature. The light one is the one that we obtain now for an axion-like particle, assuming that, considering the conversion probability of this axion into photons in the stellar magnetic field. And the dashed line is the result for, again, a specific UCD axion, the case visit UCD axion. So you see that these two bounds are roughly similar as we were expecting, but now we are able to probe much larger axion masses. And so we are getting closer and closer to our goal, touching these theoretical predictions here. All these bounds, again, were obtained looking at supernova 1987A with the solar maximum emission. So what if we start now studying the case of a future galactic supernova? So let's take this future galactic supernova to be at a distance of roughly 10 kiloparsec. And in our work, we studied two possible scenarios. The scenario where we have a supernova similar to supernova 1987A. So again, a blue supergiant progenitor star with a radius of 45 solar radii. We vary the magnetic field strength between 0.1 and 10 kilogauss, and we model it as a perfect dipole field. We assume that the supernova goes off directly above Fermi-Lat. So we just model our detector response as for Fermi-Lat. And then we also studied the case where the progenitor is a red supergiant with a much larger radius. And here, of course, the magnetic field is more complicated, and we had to rely on hydrodynamical simulation. We had to account for the photon optical depth, and we used the equipartition theorem to model the magnetic field. So for the first case, the case of a blue supergiant, these are our results. So you can see, again, the plot I showed you before in orange, and now our projections in red. So the dotted line is a projection for an axion-like particle. And the solid red line and the red band are the two projections for two different UCD axion models, KSVZ and the FZ. Now you can compare with the theoretical prediction. You see that in both cases, we intercept this theoretical prediction at some point, meaning that we would be able to probe all axion masses above, let's say, roughly 10 to the minus 5 EV. So this would be a great result. Now, to extract these projections, as I said, we assume that the supernova goes off directly above Fermi-Lat. And we model the detector response as Fermi-Lat. Now, the chances that Fermi looks at the right place at the right time in case of a galactic supernova today are actually really low because of the field of view of the instrument at downtime during its orbit. So we propose to have what we call a galactic axion instrument for supernova, which is nothing else than a full sky constellation of small gamma ray satellites that allow to continuously monitor the full sky in the gamma ray spectrum, in particular in the region of interest for us, which is between 10 MeV and 1 GeV. We started discussing this with Dr. John Tomsic from the Berkeley Space Science Laboratory, who came up with the idea of having a relatively inexpensive concept using a constellation of multiple 16 units CubeSats, each one equipped with multi-layer bismuth germinate scintillators and scintillating fibers read out by silicon photomultipliers. And we very recently got some private funding to start R&D on this. So John is taking care, of course, of doing the R&D for the instrument, and we are working on improving on our theoretical prediction for both action emissivity and conversion into gamma rays. So I leave you here with my conclusion, which are nothing else than I think supernova offer a unique way to look for QCD action and in general action like particles. We found that there are several production mechanisms that compete in the core of the star and have to be taken into account. The conversion of action into photon is what can give us a very powerful probe. Of course, we need to consider conversion in the magnetic field of progenitor stars. So what we would actually need are state-of-the-art magneto-hydrodynamical simulation that allow us to properly account for this conversion probability. And since we started working on this idea of having a network of gamma ray telescope, we are really interested in listening new ideas or different ideas on how on other or different physics scopes for this kind of experiment. At the moment, for instance, we are thinking about looking for neutron star mergers, where you would expect also a gamma ray signal coincident with the gravitational wave signal, given the large temperature and densities that are reached during this process and the large magnetic fields in which you can convert action into photons. Thanks a lot.
Any questions for Claudio? Oh, Federico has a question.
I don't know if you can hear me.
Yes, yes, I can.
So you showed the plot of the coupling constant in the solar environment. I'm just curious. So the density inside the sun is much lower than the neutron star density. But what will be the level of flux expected in axions from a quiescent solar situation? For Fermi, so is the Fermi energy band? Is the flux has been calculated? I don't know.
For the sun.
Yeah, just for this.
For the sun, I'm sure it is. I don't have the answer on top of my mind. But we are also probably talking of a much lower like energy, right?
Fermi.
No, from the sun, I mean, because what we need, so for this spectra, what we needed was really temperature very high, like temperature reached in a supernova environment.
But there is an excess from the solar disk in Fermi lab.
Oh, I see.
Yeah. So in units, it's in terms of flux, is a few orders of magnitude smaller than the impinging flux of galactic cosmic rays at 1 AU.
Okay.
So there is some number. So since there is an open question about the solar excess, the excess for the solar disk in the gamma ray range of spurious reactions, could have any contribution?
I see. I don't know the answer to this question. But
Yeah.
Maybe let's chat later.
yes, okay.
Okay, any more questions for Claudio? If not, I have a question. So, can you run us through what you did that was different for the first interpretation of the Supernovae 1987A results? Because this has been an object that has been studied to place constraints on axions for a long time. So can you just conclude as
Yeah, so there are mainly two points here. So the first one is that people in the past just looked at action emissivity through Primakov processes. What we did was to properly account for all of this. Okay, of course, to do all of this, for instance, you need to know something about the number density of pion in a supernova. And this is, of course, debatable in the sense that it's not clear if you have pion condensate or not. So there are uncertainties here. Definitely not on this diagram, which was in any case neglected before. And the second point is just the fact that sorry, let me. Yeah, good. So now the dark orange region is the one in the literature, and our region would extend just to larger masses once you properly account also for the conversion probability in the stellar magnetic field. While previously people just looked at conversion probability in the galactic magnetic field.
Yeah. And Yeah, so what are the observation constraints from this data from 1987 that you used to?
Oh, yeah, I can show you. I think I have the data. Let me show you. Yes, so these are the three energy beams studied by the solar maximum mission. So here I'm showing you the signal mode. So, okay, these are the data. And I don't know if you can see it. For instance, you can see it here. This is the signal model for our best fit. Okay, so what we did was we just, so these are the data again. So what we did was we modeled the background as just a linear function of t plus a constant, and we convoluted our axion emissivity with the detector response, the effective area of SMM. And then what I'm showing you here is just the best fit of our signal against the data.
Yeah, so it's a time evolution.
Just time evolution, yeah, absolutely.
Okay, thank you. Any more questions for Claudio from the room or from Zoom? Okay. Well, in that case, let's thank Claudio again.
Thank you.
And just as a reminder, next week, we have Professor Chris Reynolds visiting. Chris is a PI of Axis, and I've just shared the meetup spreadsheet a few minutes ago before the seminar, if you would like to sign up. Yeah, thank you. Have a good week, and thanks for all who made it, and we're still preparing new start proposals.